Welcome to the Explainer. We're always dealing with lists of things that are constantly changing, right? So, how do you find the most important item without having to search through the entire list every single time? Well, the answer is a really clever data structure called the heap. And today, we're going to build it from the ground up. Okay, so here's our game plan. First up, we're going to see how a tree can actually hide inside a simple array. It's super cool. Then we'll define what a heap is. After that, we'll get into its core moves, adding and removing things. We'll see it all come together in heap sort, and then we'll wrap up with why this thing is so darn important in the real world. All right, first things first. We gotta understand the foundation of a heap. And it all starts with this brilliant trick for representing a binary tree. Not with all those messy pointers and nodes, but with something way, way simpler. We all know this picture, right? The classic binary tree. You've got the root at the top and all the children branching down. It's visual, it makes sense. And we definitely know what an array is, just a flat line of items in a list. But what if I told you we can take that entire complex tree structure and store it perfectly inside this simple flat array? So that's the big question, isn't it? How do you keep track of who's a parent and who's a child when everyone's just standing in a single file line? If you're at some random spot in the array, how do you find your parent? The secret isn't some complex tracking system. It's just a little bit of beautiful, simple math. And this right here, this is the magic. Seriously, forget about pointers. We just use an element's position, its index, to figure everything out. Let's try it. Say we're at index 3 in a zero-based array. Where's its left child? We just calculate 2 times 3 plus 1, which is 7. Boom, the left child is at index 7. What about its parent? We calculate floor, 3 minus 1 over 2, which is 1. Its parent is at index 1. It's that easy. With these formulas, we can jump around that tree structure perfectly, even though it's just sitting in a flat array. Now, for this whole array trick to actually work, the tree has to have a very specific shape. You have to fill it up level by level from left to right with absolutely no gaps. This dense, packed-in structure is called a complete binary tree, and it is the mandatory, non-negotiable foundation for a heap. So, we've got the structure, right? The complete binary tree living inside an array. Now we just need to add one simple but incredibly powerful rule to turn it into a heap. So let's make this super clear. A complete binary tree is all about the shape. That's it, no gaps. A heap, on the other hand, takes that exact same shape and adds one crucial rule about the values you put inside it. And this is the rule. It's called the max heap property, and it is so simple, it's brilliant. Every parent has to be bigger than or equal to its kids. That's the whole thing. And this one little rule gives us a massive payoff. The biggest, baddest element in the entire collection is always guaranteed to be sitting right at the top, at the root. Okay, but that's great when everything's just sitting there. What happens when we actually want to change the data? If we add or remove something, we might break that rule. So the heap needs a couple of special moves to fix itself and get back in order. So let's say we want to add a new element. First, we just stick it in the next open spot at the very end of the array. That keeps our tree complete, but it might be bigger than its parent, breaking the rule. So we check. If it is bigger, we swap them. And we just keep doing that, swapping our way up the tree, a process people call bubbling up, until our new element finds its rightful place and the whole heap is happy again. And removing the max element, well, it's pretty much the exact opposite. We can't just leave a hole at the top, right? So we take the very last element in our heap and move it all the way up to the root. Now that new root is probably way too small. To fix it, we sink it down the tree. We keep swapping it with its bigger child until it finally settles into a spot where it's larger than the kids below it. It's this perfect symmetry. Insertion bubbles up, deletion sinks down. Now this whole elegant process, always being able to find and remove the biggest element, is the engine that drives one of the most famous and efficient sorting algorithms out there, heap sort. So let's picture it. We start with a totally jumbled, unsorted array. The very first step of heap sort is to organize this mess into a proper max heap. This setup process is called heapifying the array. We're basically just shuffling things around until every single parent is bigger than its children. Okay, once we have that valid max heap, we know for a fact where the biggest element is. It's at index 0. So we do a little switcheroo. We swap that biggest element with the element at the very end of the array. And just like that, the biggest element is now in its final, correct, sorted position. We can basically lock the door on it and pretend it doesn't exist anymore.
We just shrink our view of the heap by 1. The sorted part of our array is now growing from the back forward. Of course, that element we moved to the top has probably broken our heap property. But hey, no problem. We know exactly how to fix that. We just run our sync down procedure on the slightly smaller heap. Once it's fixed, the new biggest element is at the top, and we just repeat the cycle, swap it to the end, lock it, and sync the new root down.
We keep doing this, swap, sync, shrink, swap, sync, shrink, until our heap is empty. And what we're left with is a beautifully sorted array. Now, this algorithm runs in what's called O(n) log n time. The n part is because, well, we have to touch every single element to move it. The log n part represents the height of our tree. That's the maximum number of swaps we'd ever have to do for any single sync down operation. It's an incredibly efficient and reliable way to sort things.
Okay, so heap sort is awesome, for sure. But is that all a heap is good for? No way. This is the why you should actually care part. Where does this stuff show up in the real world? The absolute killer app for a heap is something called a priority queue. Think about a hospital emergency room. They don't treat patients first come, first served, right? They treat the person with the most critical injury first. That's a priority queue. And a heap is the perfect way to build one because getting the highest priority item is ridiculously fast. It's always just sitting right there at the root waiting for you. And these priority queues, they are the secret workhorses of computer science. I mean, they're everywhere. Your computer's operating system uses one to decide which program gets to run next. Network routers use them to find the fastest path to send your data across the internet. They are absolutely fundamental to everything from data compression to running massive complex simulations. And that's really the heart of it. That's the power of the heap. It's this beautifully simple data structure that's designed to do one thing exceptionally well: give you instant access to the biggest or smallest element in a constantly changing set of data. So the final thought is this: anytime you have a problem that's all about repeatedly finding the best or most important item from a dynamic list, a heap should be the very first tool you think of. So what problems in your world could that solve?